Everyone. This is in continuity with the paper 5054/22, October November 2022, physics paper 2 theory. And I'm going to do this question. An uncharged plastic rod is rubbed with an uncharged woolen cloth. As a result, the rod becomes negatively charged. Explain in terms of particles how the rod becomes charged and state what is going to happen to the cloth. So, okay, so what will happen? It's going to be like during rubbing, when it's going to be like friction, when the rod is going to be rubbed with the woolen piece of cloth. During rubbing, the electrons will be uh, transferred from woolen cloth to plastic rod. This is what will happen when you rub this thing. Okay, now second thing is going to be the rod becomes negatively charged, and the woolen cloth will be positively charged. So I hope you got the concept. Figure 8.1 shows a metal sphere X on a plastic stand. Explain why metals are electrical conductors and why plastics are electrical insulators. So obviously, you know this thing that the metals have free electrons. Metals have free electrons, or you can say delocalized, or sea of electrons that helps in the flow of electrons. Or you can say it's better to write charges rather than electrons, because the electric current can be either flow of protons, or it can be either flow of electrons. So in the category of charges, when you say charges, so it means it can be either it can be electrons or it can be protons as well. So plastic, the second point what we are going to write is plastic don't have these free electrons, so don't have these, so they are insulators. Okay, now moving to the next question. And if the question states that the negatively charged plastic rod is held above sphere X. Figure 8.2 shows that it does not touch the spheres. So by drawing on figure 8.2 shows the distribution of charges on X. So what will happen? The positive, initially this sphere is going to be neutral. So all these positive charges will be attracted towards the negative, and the negative will be repelled, because those are like charges which are going to be repelled, and unlike charges are going to be attracted to this thing. Okay, an earth wire is now connected to the metal sphere as shown in the figure. Okay, state what happens to the charges on the sphere as the earth wire is connected. So what will happen? Negative charges will flow in ground, and the positive will remain on the top. Positive will remain on the top because of the electrostatic force of attraction of the negative charges, top of the sphere. Okay, so this is we are done. Let's go to the next question. And the next question states that the earth wire in 2 stays connected in the metal sphere. Describe the distribution of charges on the sphere. So again, on the top there will be positive charges, and on the bottom it's going to be negative charges. So this is what you have to write it over there, and be sure that the time is of crucial importance. So you guys have to see how you are writing this. The earth wire is disconnected from the sphere, and then negatively charged rod is moved away from the sphere. Explain what happens to the charges on the sphere as charged rod is moved away. So what will happen? The charges will distribute evenly in sphere. Okay, so the whole sphere will become whole sphere is going to be positively charged. This is what is going to happen. A second metal sphere Y is negatively charged. There is electric field surrounding Y. State what is meant by electric field. So electric field is a region or a space around which another charge experiences a force of attraction or repulsion. Force of attraction or repulsion. Okay, shows negatively charged sphere particles. So this is the negatively. So all the arrows is going to come towards this. So this is what you have to draw. Okay, this is I have already done this question. Now moving to the next question is going to be protactinium. Protactinium 234 is a radioactive isotope of protactinium that decays to uranium 234. Compare the nuclide notation to 23491 Pa with the nuclide of the uranium and deduce what this shows about what is emitted this and this. Place a tick appropriate box to show what is going to happen. Okay, so what is going to happen is an alpha particle is emitted. Again, uh, let me check. Now you see this thing that over here this number is 91 and over here this number is 92. So basically this has increased by 1, and in the alpha particle it's not like this. So whenever you have for example, if I talked about this thing that the proton number is if increased by 1 as compared to the previous one, as compared to nuclei parent nuclei, then it's go and second thing is this, that the nucleon number does not change. Nucleon number does not change. So this means that it's a decay or beta radiation. So in this case, this is alpha particle cannot be possible because it's an addition of +1, yes, and we don't know the exact. It's not possible to tell because the required information is not completed. The most abundant isotopes of protactinium than this is this, explained by referring to their nuclear composition, why protactinium and protactinium are both isotopes of the same element. Okay, so now you have to tell them that both have same number of protons, same number of protons and different number of neutrons. So I was telling you that both have same number of protons and different number of neutrons in their nucleus. Then there is a question explained by referring to their nuclear composition why protactinium 231 and the protactinium 234 are different isotopes of element. So now you see in the case of 231, it has 91 protons and 140 neutrons. So you subtract 231 out of 91, you will get 140. And in the case of 234, they have again it has same number of protons, which is 91, and neutrons is different. 234 minus 91 is going to be 143. Another teacher places a radiation detector on a bench in a school laboratory and switches it on. The teacher must measure and record the background radiation count rate, describe what is meant by background radiation, and states two significant sources of the count rate recorded by the teacher. So, what is background radiation? It is always present in our surrounding, and this is due to SURROUND surroundings, and this is due to cosmic rays due to sun, or might be the rocks they are emitting those radiations. Okay, now coming back to the next question, the teacher moves the sample so that it is next to the detector. Suggests one precaution that ensures the sample is moved in a safe way. Okay, I'll write a few of the precautions so you guys can remember or memorize any one of this. Use special tongs or tweezers, forceps. You can write any. Oh, sorry, my bad. Forceps is forceps. Okay, you can use goggles to avoid anything going into your eyes. Keep a safe distance. Keep distance from the radioactive device, and you should have a specialized lab coat. Specialized lab coats, etc. So anyone would be perfect for you. Okay, now this is the graph shows the correct count rate against the time of the radioactive sample. The curve is the best fit line. Explain why many of the crosses do not lie on the crosses. Because the radiation is what? Radiation is a random process. And the second thing is this, that the readings are fluctuating means that whatever the instrument is used to detect these radiations, so they are going to be like it's fluctuating, it's varying, it's getting different answers. Use figure 9.1, determine the half-life of the protactinium 234, show your working. Okay, now what you have to do is you have to, let me go back, and you have to determine the background, I'm sorry, it's you have to find out the half-life of this. So I have done the working over there. So it's going to be like 58 divided by 2 is going to be like 29, and on x-axis if you follow this is going to be 29. So if you follow the curve like this, so you have to find out the value from here. So whatever the value is over here, so you have to write it over here. So in the marking scheme it is between 66 to 73, so you guys can easily find out in this. The uranium 234 formed from the protactinium 234 is also radioactive. Its half-life is many thousands of years. Explain why radiation from uranium 234 does not affect the count rate measured in this experiment. It's basically our sample space, or the graph which we are taking is for only our sample space, or the graph is only for 320 seconds, because I know that the half-life of uranium is 5700 years. So you might be memorizing this number as well, because if you memorize this, then you will be able to understand this question, that because our sample, or this question that is given in this paper is basically for 320 seconds, so we cannot find out this as compared to 5700 years. And this is going to tell us that this is a slow decay rate, and then it's going can't be expressible on such small graph, can be expressible in this graph. So thank you very much.